All right, we have section 2-5, zeros of polynomial functions, day 1. After this lesson, you should be able to identify the zeros of a function by either factoring or using synthetic division, and use the zeros to sketch the graph. So we're going to start with the definitions. The first one, the definition of standard form of a polynomial. It says, shows any like terms, combines, and the terms arranged by degree in descending numerical order. It basically means it's simplified as much as possible. There aren't any other like terms to simplify or to combine. And that the degrees are written from the highest power down to the lowest, so descending numerical order. The leading coefficient, as long as your polynomial is written in standard form, the leading coefficient is going to be the non-zero factor that is multiplied by the greatest power of x. In other words, it is the coefficient that is in front of the term that has the highest power. The degree of the polynomial, again, as long as it's written in standard form, the degree of the polynomial is the greatest degree of any terms. It should be the first one, as long as it's written in standard form. So let's go ahead and get started on example number 1. It's asking us, what are the zeros of each function? Now, the zeros of the function, that's another way of asking you to find the x-intercepts, or another way to find the x-intercepts. It's also asking you to find the solutions or the roots of the function. All of those words mean the exact same thing. So let's start off with part A. It says, what are the zeros of each function, and graph the functions. So we're starting off with the function f of x is equal to x times x minus 4 times x plus 3. This polynomial function right now is written in factored form. All of it is factored completely. We can't factor it any further. So this is factored form. And what's nice about it when it is in factored form is we can jump straight to finding the zeros. We don't have to factor first. That part is already done for us. So when it says, what are the zeros of each function? Another way of saying that is, what are the x-intercepts of the function? So in order to find the x-intercepts, where your graph crosses the x-axis, we just plug in a 0 for y. So the f of x here, instead of f of x, we're going to put in a 0. So I have 0 is equal to x times x minus 4 times x plus 3. At this point, we can use what is called the zero product property, as long as it's factored completely, which it is already. So we're going to use the zero product property, which tells us that we can take each of those factors, which you can see there are 3 of them, and set them equal to 0 and solve. So I'm going to go ahead and take the first factor, which is just that value of x right in front there. So I'm going to take that first factor and set it equal to 0. So x is equal to 0. And I'm going to take that second factor, which is the x minus 4, and set it equal to 0. And then I'm going to take that third factor, that third binomial, and set that one equal to 0. So we have x plus 3 is equal to 0. And now we can go ahead and solve. And these are going to give us our zeros of the function. So the first one is actually already solved for us, right? X equals 0. There's no other work that needs to be done there. So there's one of our solutions. The second one, though, we do need to add the 4 on both sides. So we get x is equal to positive 4. And the last one, we need to subtract 3 on both sides. So we get x is equal to negative 3. Oops, x is equal to, let me erase that. X is equal to negative 3. All right, so we have our 3 x-intercepts, or the zeros of the function. So I'm going to go ahead and plot those because our goal is to graph this function. So that was one piece, was finding the zeros. We found that there were 3 of them. That means our graph is going to cross the x-axis at all 3 of these points. So the first one, x is equal to 0, is right here on the origin. X is equal to positive 4 right here, and x is equal to -3. So now I've plotted the x-intercepts there, or the zeros of the function. So the other thing we need to know in order to graph the function would be its end behavior. So if you remember back to end behavior, we look at the function in standard form. So I need to take this function, which we had in factored form, and I need to figure out what it would be in standard form, because we need to know the leading coefficient and the degree of the polynomial. So if I was to multiply this out, we have the x multiplied by the x minus 4 multiplied by the x plus 3. You can pick any two at a time that you want to multiply. I'm going to go ahead and multiply these two together first. Actually, I'll do it over here. Okay, so I'm going to multiply those two together first. I'm trying to get this in standard form. So I have f of x is equal to x. And when I multiply those out, we have x times x, which is x squared. Right? X times x is x squared. X times 3 would be 3x, but then we have -4 times x. Combine those and I just get -x. -4 times 3 gives me +12. So plus 12. Then I need to distribute that x to all of those pieces. And when I do so, I just get x cubed minus x squared plus 12x. So this is our function in what we call standard form. And standard form helps us figure out the end behavior. So if we are looking for the end behavior, remember there's two things that we're looking for. I'm going to write end behavior over here. We first need to know what the leading coefficient is. So the leading coefficient in this case is this +1 right here, right in front of that x cubed, as long as you wrote it from highest degree down to the lowest. So the leading coefficient is a 1, and 1 is positive. The degree of the polynomial, and again, as long as it's written in standard form, it's the first one. It's the highest power, is a 3. That is odd. So if we know that the degree is odd, and we know that the leading coefficient is positive, we know that the one side of the graph is going to be pointing down and one side of the graph is going to be pointing up. So I always think of a linear function. A linear function is the easiest odd function. And when you think of a linear function, I'm just going to draw a linear function over here. If you have a linear function drawn like this and you have a little person walking from left to right, they are walking up the mountain, this would be positive odd. So if we have a linear function that looks like this, again, the little person walking, this time they are walking down the mountain, that would be the negative slope. Okay, so since our function is positive and odd, we know that it's going to look like this, okay, which is what our function. So the left end is pointing down. So in other words, as x is approaching -infinity, as we're looking at it to the left-hand side, the y value is also pointing down. So the y value is also pointing to -infinity. And if we look at it to the right-hand side, as x is approaching +infinity, the y value is pointing up. So the y value is also approaching +infinity. So I'm going to go ahead and draw the end behavior on our graph here using the roots, right? Using those zeros of the function. So if we know that the left-hand side of the graph is going to be pointing down, that means I'm going to go to the left-hand 0, the one that's all the way to the left side, and I'm going to draw an arrow pointing down from that. And then I know the right end behavior is pointing up, right? Y is going to approach +infinity. So on the right-hand side here, I'm going to draw an arrow up. Now, what happens in between? Well, this is where we're just going to sketch it. We don't need to know exactly what the local maximum or local minimum is right now. We're just going to sketch the graph. So I know that it passes through this point. The graph passes through that because that was an x-intercept. And then I know it has to turn around at some point and pass through this x-intercept. And it has to turn around at some point and pass through this x-intercept. It's basically connecting the dots. So basically reviewing, the two things we need to know in order to graph a function is the zeros of the function and the end behavior of the function. So let's go ahead and try another one. Part B, I'm going to copy down the problem that was written up above. Get the gray here. All right, so this function is written as g of x is equal to x to the fourth minus 81. G of x is equal to x to the fourth minus 81. That function is in standard form, right? So part A was given to us in factored form, which was nice because it helped us find the zeros. This one is given to us in standard form. Standard form helps us find the end behavior. So on this one, instead of starting by finding the zeros of the function, I'm going to start by finding the end behavior. Okay, so remember, the end behavior all depends on the leading coefficient and the degree of the polynomial. So if we're looking at the end behavior, the leading coefficient here, it is written in standard form, meaning the highest degree down to the lowest. There's only an x to the fourth and a constant. So the leading coefficient is this one directly in front. So the leading coefficient is a positive 1. It is positive. And the degree of this polynomial is 4, which is even. So remember, whenever the degree is even, that means either both ends are up or both ends are down. Well, because it is positive, if you think of a quadratic, if you have a positive parabola, a positive quadratic, it's a smiley face. That means both ends are going to be pointing up. So it's going to look like this. So if we use our mathematical terms, as x is approaching negative infinity, in other words, as we're looking at the graph on the left-hand side, the y value is pointing up. So the y value is approaching positive infinity. And as x is approaching positive infinity, in other words, as we're looking at it to the right-hand side, the y value is also approaching positive infinity. So again, standard form helps us find that end behavior. So now we need to go ahead and find the zeros. But in order to do that, it needs to be in what we call factored form. So to do factored form here, we got to think back to all of the methods that we learned in the past. And we have our product sum, which is usually done if it's a trinomial. We have difference of two squares, which has a subtraction sign, a perfect square and a perfect square. We have sum of cubes, we have difference of cubes. But this one, since there is a subtraction sign in between two perfect squares, x to the fourth is a perfect square, and 81 is a perfect square, I'm going to use difference of squares in order to factor this. So difference of squares. All right, so instead of writing it as x to the fourth minus 81, I'm going to rewrite it as two binomials where one has an addition sign in the middle and one of them has a subtraction sign. It doesn't matter which one you put where, because multiplication is commutative. So now I need to take the square root of x to the fourth, which gives me x squared. So that's going to be my first term on both of these. And the square root of 81 is 9. So that's going to be in the second term on both of those. Now, before we say we're finished, we always have to make sure if there's anything else that we can do to factor any further. The x squared plus 9 cannot be factored further, so I'm going to leave it alone, x squared plus 9. But the x squared minus 9, since there is a subtraction sign there, that again is another difference of squares. X squared is a perfect square, 9 is a perfect square. So it's going to factor into two binomials where one has a plus and one has a minus. I'm going to take the square root of x squared, which is x, the square root of 9, which is 3. And now this one is written in factored form. So this is when we can use the zero product property. So I'm going to go ahead and get my pencil again. So if we did this zero product property, that's telling us that we can set the entire polynomial equal to 0. In other words, we can take each function itself, or each factor, and set them equal to 0. So my first factor is the x squared plus 9. So I'm going to write x squared plus 9 is equal to 0. My second factor we have is x plus 3 equals 0. And the next factor we have is x minus 3 is equal to 0. So I just need to solve for each of them. None of them are solved already. Now on this first one, if I subtract 9 on both sides, I end up getting x squared is equal to a negative 9. Now how do we undo something squared? All right, so how do we undo something squared? We have to take the square root of both sides And that's going to give us two different answers. So we have to put a plus or minus here. So this is going to give me x is equal to plus or minus. Now, because we have this negative underneath the radical, it's an imaginary number. So the square root of 9 is 3, and the square root of a negative is imaginary. So we end up writing plus or minus 3i. Okay, so on the next one, I'm going to subtract 3 on both sides. We end up getting x is equal to negative 3. And this one, if I add 3 on both sides, we end up getting x is equal to positive 3. Now, anytime you have an imaginary solution, or a complex solution, the complex solution are not zeros. So even though we are going to get 4 solutions total because it does have a degree of 4, here we have 1 solution, 2 solution, the x minus 3 is a third solution, x equals positive 3 is our 4th solution. The imaginary numbers cannot be graphed on a real number axis. So we have an x-axis and a y-axis. We can't graph an imaginary number on there. So that's okay. We're just going to go ahead and plot the 2 real zeros that we did find. So we said that there's one at negative 3. So 1, 2, negative 3. And then there's one at positive 3. 1, 2, positive 3. By the way, they did ask us to find the zeros, so I'm going to box those as my answers. Okay, we already know the end behavior. So I know that from the x-intercept, that's all the way on the left-hand side, our end behavior is going to be pointing up. It points to positive infinity as well. So I'm going to draw an arrow up. And then from the x-intercept on the right-hand side, I am also going to draw an arrow up. Now, what happens in between there? We could find the y-intercept to find exactly where it crosses, but we're just sketching the graph here. So I know that it has to come down, and at some point it is going to turn around and pass through this x-intercept as well. It does not have to be exact. The 2 things that we're really working on is finding the end behavior and finding the zeros of the polynomial. I am going to write a little note down here that you should write on yours as well, that complex zeros, which are imaginary numbers, complex zeros are not x-intercepts. Okay. Okay, so that brings us to our last example, which is going to be change it up just a little bit. If you notice, the one thing that is different on here is that we have an inequality instead. We're still going to start off by doing the same thing. We need to figure out what the end behavior is going to be. Okay, just in the end, how we write our solution is going to be a little bit different. All right, so we're starting with the cubic binomial of x cubed minus 16x. If you look at x cubed minus 16x, on the right-hand side here, it says less than 0. So basically, when we are looking for less than 0, we're looking to see where is it below the x-axis. Okay, so less than 0 means where is our graph going to be below the x-axis. So in order to do that, we have to graph it. So this means negative. We want to know where is it going to be below the x-axis. Sorry, my writing is sloppy on here. Okay, so we're going to go ahead and start by finding the end behavior, just like we did on the last 2 examples. So with the end behavior, we need to make sure it's written in standard form, which it is. So if we look at the standard form, we have x cubed minus 16x. We're just looking at that left-hand side there, as long as the 0 is on the right-hand side. So if we're looking at the end behavior, again, we need the leading coefficient, and the leading coefficient in this case is a 1, which means it is positive. And we need the degree of the polynomial, which in this case is a 3, so that is odd. So odd positive, just like example or the first example that we looked at today, example 1a. Okay, so if it is odd and positive, odd means one end is up and one end is down. If it's positive, think of a linear function. The left end is pointing down, the right end is pointing up. So then we need to find the zeros of the polynomial. In order to graph this, again, we have to have the end behavior and we have to have the zeros of the polynomial. So if we are looking at the zeros, we need it to be in factored form. Okay, so right now we have x cubed minus 16x is equal to 0. We want to change this into factored form. If you notice, both of those terms there have an x in common. So I'm going to take out their GCF, their greatest common factor, that x. And if I did, I would then have x squared minus 16 remaining. Always double check to make sure you are completely finished factoring before you use the zero product property. So in this case, it is a difference of squares problem, right? There's a subtraction sign in between. X squared is a perfect square, 16 is a perfect square. So I end up writing x plus 4 and x minus 4. So we have three different factors here. In order to find the zeros of the polynomial, I'm going to take each factor and set it equal to 0. So this first one is just x. X equals 0. The second one we have, trying to get a different color, we have x plus 4 is equal to 0. And the third one, we have x minus 4 is equal to 0. So I'm going to set each of those, or I'm going to solve for each of those. This one's already solved for. This one, all I need to do is subtract 4 on both sides. We get x is equal to negative 4. This one here, I'm going to add 4 on both sides. So we get x is equal to positive 4. So that means our graph is going to cross the x-axis at all three of those points. Okay. I'm going to move this up just a little bit so you can see my graph down below. Okay, so I'm going to go ahead and graph the zeros of, or the roots there. We have one at x equals 0, which would be right here. We have one at x is equal to negative 4, and we have one at x is equal to positive 4. And remember, if we go back up to our end behavior, the left end is going to be pointing down, the right end is pointing up. So let me go ahead and draw that. The left end we said is pointing down. The right end is going to be pointing up. So what happens in between? This graph is very similar to part A, example 1, part A. It's going to pass through this point. It's going to make a U-turn, pass through this x-intercept, make a U-turn, and pass through this x-intercept as well. Now, if this were just an equation, we would be done, right? If it was just a function, we would be done. But this one is an inequality. Notice it is saying less than 0. So basically they're saying, look at your graph and tell us the interval where it is going to be less than 0, where it is underneath the x-axis, below the x-axis. So again, I'm going to write here, we are looking to see where is the graph below the x-axis. And again, we're looking to see where it is below the x-axis because of this symbol here, because it was less than, okay? So let's look at our graph. I'm going to highlight the piece where it is below the x-axis. You can see there's two different sections. We've got a section here that is below the x-axis, and we have this section here that is below the x-axis as well. Now, it's not asking for the zeros of the polynomial, of the function. It's just asking where is it below. Okay, so this end is going to be pointing down forever. And notice it's slanted to the left just a little bit because eventually it's going to hit all x values to the left. That means it's all x values starting at negative infinity until we reach this 0. So if you notice here where it crosses the x-axis, once it hits that 0 there, it's called a 0 because it's not below and it is not above the x-axis. It is on the x-axis, so it's not going to be included in our solution because our solution, we just want where it is below the x-axis. So remember, I have to put the parenthesis there. Now, there's a second interval in which it is also below the x-axis, so I'm just going to put an and sign here. And the piece where I highlighted, you always want to write the smallest number first. So if you look here, the next 0 is at 0. So it's not including that number, it just starts there. So I put a parenthesis. all the way until we reach this 0 on the right-hand side, which is at positive 4. So notice the zeros of the polynomial also help us figure out where the graph is going to be above or below the x-axis. So this then is our solution. This is what we're looking for with an inequality. Now, it's not always going to say less than. It can also be a greater than symbol. And if there was a greater than symbol, then you would be looking to see where it is above the x-axis. So make sure you pay attention to that. Also, you want to make sure that the 0 is on the right-hand side. So if for some reason they gave it to you backwards, just flip it around by like taking your paper and flipping it over. So your homework this evening is on page 97. You're going to do numbers 2, 12, 13, 22, and 23.